take a look at this. What sort of eigenvalues am I getting now? Repeated. When it's repeated, what am I going to have to do? I'm going to have to find a generalized eigenvector, and that's the game. So this is a problem that we've done. What I'm going to do now is I'm going to scoop up all of this stuff that we've done in the past. And then I'm going to send it to the trash. I'm going to grab this solution. Then I'm going to take some notes before I start drawing. Notes. First note. As t goes to infinity, what happens to my solution? As t goes to infinity, what do all these exponentials do? They decay to 0. Okay? Even this even this term in the solution decays to 0. Even though I have that t multiplier, right? It still decays to 0, and that's because of L'Hopital's rule. So I know everything is going to the origin. So everything going to the origin, this is feeling like a sink, right? There's some sort of sink going on here. But I want to know what happens really far forward in time. If I'm going really far forward in time, all of these exponentials in the limit will go to 0, but really far forward in time, all of these exponentials are getting smaller. Let's call this term 1, term 2, and term 3. When I pit these things in the future battle of t getting very, very large, which is going to outlast the rest of them and just struggle to stay non-zero even when time gets really large? Term 1, term 2, or term 3? Which is going to outlast the rest? Okay, getting some chats coming in. People are saying term 2. All of these terms are decaying, but because of this t multiplier on term number 2, it's got a little extra bit of something hanging out at the very end of time. Okay? So as t gets really, really large, x of t is going to basically be guided by this dominant second term, plus a little bit of stuff from the rest, right? But basically it's going to be the second term. Now, we reverse the argument and say, let's look at the history. Let's look at what had gone on in the past. If t is much, much less than -1, what are all of these exponentials going to do now? They're all going to blow up, right? And as they're blowing up, term 1, term 2, or term 3, which is blowing up hardest? So all the exponentials are growing, but this exponential has a t multiplier, and if that t is a really big negative number, do you see that that t multiplier gives this one a little bit of oomph, right? And that little bit of oomph means that even far backwards in time, it's the second term that dominates. And then there's a little bit of extra stuff from the other terms. Okay? Now compare that to our previous examples where we had one eigenline drawing it in and then another eigenline directing it to the finale. Here, term 2 wins really far in the future, and term 2 wins really far in the past. So what that means is that it is this eigenline that is directing the behavior of the styrofoam peanuts really far forward in time and really far backwards in time. So let me get an axis set up Here's an XY coordinate system. And now, in purple, what is the line 0, 1? Well, isn't it this vertical line right here? It's just a continuation of j hat. Now, how should the arrows point on this one and only one eigenline? Yep. Term 2 controls everything deep in the future, deep in the past. Where is everything going in the future? The arrows are red, and so they point into the origin. Terms 1 and 3, that's a good question in chat. The question is, when does terms 1 and 3 matter? Well, when t is equal to 0, it's the only time when the second term loses any sort of effect. When t is 0, the second term's gone. And so there's this moment when t is equal to 0 between trading off between terms 1 and 3, there's this moment when t is equal to 0 where the influence of this term, which controls the deep history and the deep future, goes away. Okay? And we got a sync going on because of all these decaying exponentials. Yes, totally. The lambda being equal to -3 is what's guiding everything to the origin. So now I've got some choices. Choice number 1. Where do I got to go? I got to go to the origin, right? That's what everything's telling me. Go to the origin. Now there are two ways to do it. Deep in the past, I need to parallel the purple eigenline, but then really far forward in the future, I better come back in to the origin, right? End up there. So I could do something like this. Since there's only one line that's guiding me, I'm going to follow the line in the past and follow that same line in the future, so I would need to bend back around and be something like this. Okay? Or I could do this. Okay, so I'm going to put the two different choices up. One's green, I could do something like this. And you might not want to draw these because they're going to conflict with each other in just a second. I have two options and I got to decide which is right. That's not the best line I've ever drawn. I could do something like that. Brown or green? I've got to decide which. Any ideas on how I would sort out which of these two is happening? An initial condition? That's a good idea. Okay. Let's choose an initial condition. Let's say x vector of 0 is equal to 1, 0. Where is that? Wouldn't that just be like right here? In green? That green dot? Okay. So now I've got to figure out how is the curve going through that function. Well, check out the differential equation. This x here is some point in space. Let's choose that to be this green point. That's my initial condition. That's where my styrofoam peanut's going to start off. Well, if I take that initial condition and multiply by this known A matrix, what is that going to give me? That's going to give me x prime. So let's see that through. Let's think about that. I'm going to have x prime evaluated at time 0. What is that going to be? That's going to be A times x at time 0. What is my A matrix? My A matrix is a -3, a 0, a 1, and a -3 times my x vector, which is 1, 0. I multiply this through. I do the first row times the column, and I get a -3. And then I do my second row times a column, so that's a 1 times a 1 plus a -3 times a 0. There we go. I get a -3, 1. So what does this orange vector represent? At time 0, where am I at? I'm at green. And at time 0, x prime at time 0, that is my orange vector. And that vector is saying I move left or right. I move left. And do I move up or down? I move up. So I should be going like this. So at that point, the styrofoam peanut will be released. It should be going left and up, but I know at the end of time it's got to come back into the origin and follow the purple eigenline as it does so. So by consulting the vector field at this point, I see that I'm going up and I'm bending back around and going purple in. So which was the winner, the brown curves or the green curves? It must be the brown curves. So what are my solutions going to look like? My solutions are going to be like way back in time, parallel purple. And then way far forward in time, time will be 0 and purple no longer has any meaning. But then I'm going to go forward in time and purple grabs me again and pulls me in. So I should see curves like these orange curves. Okay? And then if I were to check a point here on the left-hand side, what I'd find out is I go down through that point. You can check the point. So I'm going purple, bending back. Okay. So is it always brown for this A matrix? Yeah, we could check a couple more points and we would find that they're always coming up through the positive x-axis, which means they need to be brought back down with the purple eigenline. And then if I check the left-hand side, they're always going down through the negative x-axis, and they're brought back up. Okay. So I'll keep an eye on chat while I code this into the visualizer. Okay. All right, so I've checked in on chat. People are now sharing things to make phone wallpapers. That's super. I'm looking at my graph here. I'm feeling it. Okay, are we ready? Visualizer change. Now, okay, what I need to tell you is that what we have cooked up here is just a sketch. These sketches tend to be fairly different than the visualizer, but we did get the rough feature, so let's check it out. Ready? Camera 2, camera 4. Camera 2, camera 4. It's tough to see what's going on here because they are fairly different, but look at these styrofoam peanuts. What do these styrofoam peanuts up here do? They go straight down into the origin. Those are the styrofoam peanuts that are on the eigenline. Now, what do styrofoam peanuts way far away do? They come in, and they've already been bent back around, and then they come up and they're bent back around finally more, until they're coming in, guided by that vertical eigenline. In our graph, we overemphasized, and that is normal and that is fine, we overemphasize the amount of bending that's going on here. That's something that a computer can really give us a clearer idea on, but we wouldn't be able to do so with graphs. But what do we know? Everything's going into the origin, right? And there's a line in space that's guiding them as they go in. And we can see some styrofoam peanuts that are moving vertically down here, and that's the eigenline. Okay. So if I zoom out, yeah, we see the same sort of pattern. Okay, so going back over to the pad, what would I call this thing? I would say that the point 0, 0 is a degenerate sink. What does the sink have to do with? That has to do with the lambda being negative. What is the degeneracy? The degeneracy has to do with there are two eigenvalues that are the same.